This is a relatively short section, but one that's of incredible importance. We address here in section 41.5 nuclear fusion and fission. And we had mentioned these before, and an example of nuclear fission is when we take U-238, 92. Remember, uranium has 92 protons, and I'm looking at that isotope of uranium because there are several. It's U-238. This is the most common one. If you dig up uranium, this is 99% of what you're going to find is U-238. And if I take one neutron, you notice a neutron has how many neutrons and protons? It has one, and it has no charge. It has no protons. So this is an interesting way to talk about the neutron in a nuclear reaction, is to say a neutron is a 1-0. One neutron, no protons. And now you can do the balance. As we look at this neutron, as we're going to throw it in at high speed and hit this uranium nucleus, what we're going to get is uranium 236 92. Of course, it's still uranium. But what have I done? 6, 7, 8. I've lost 2. And how did that occur? This is going to be U-236. Well, excuse me. If I add the 1, I made a mistake here. Apologize. I'm going to look at U-235, not U-238. U-235 is much rarer than U-238. I misread that small letter right there. This is U-235. We'll hit it with a neutron, and the 235 adds one neutron to become 236. I still have the 92 down here, and that U-236 then decays all by itself. So the neutron gets absorbed in here. Then it becomes two different elements, barium and krypton. Yeah, krypton is an element. And the barium is 56, 141, and the krypton is 36, 92. And if I take the 36 and the 56 and add them up, I'll get 92. And I also have, out of that, 3 more neutrons. I have 3 1n0s. That's how we write that. If we have more than one of something, we write it as 3 times that or 2 times that. So I have taken this uranium, basically, thrown in a neutron. It became excited, it decayed, and it split apart into 2 almost equal. The barium is somewhat larger than the krypton, but it's split into almost equal nuclei. This is what is called splitting the atom. And this U-235 is a very fissile element, and it's easy to break it apart. And you'll notice that I started out with 1 neutron that I threw in, and I get 3 neutrons when I come out. Whoa, that means I can get a chain reaction. Because if 1 starts this, then this produces 3 more, and then those 3 can make 9 more, and so forth. Okay, well, this is an example of a heavy nuclei that's split into 2 or more stable nuclei with an energy release. Of course, there's plus energy. A lot of energy comes out with these neutrons. Now let's look at a different type of thing. This is called fission. Now let's look at fusion. Here I'm going to take hydrogen, 1, 2. Well, what is that? That's not regular hydrogen. Most regular hydrogen is just 1 proton, and that's it. Well, this is a proton and 2 neutrons together. This is a very heavy form of hydrogen, plus 1 H3. That's 3 neutrons and protons. So this is going to have 1 proton and 1 neutron. This has 1 proton and 2 neutrons. And these are going to make up a helium 2. That's the 1 and the 1 is the 2. And 3, 4, 5, but it doesn't. It makes helium 4. And I got a neutron out of that. 1 neutron. And so you can see that 2 plus 3 is 4 plus 1 is 5. So I've got the same number of neutrons and protons. and here I have a 1 and a 1 balancing the 2 that's over here. And this is what happens in stars. The hydrogen, under very, very high temperatures and pressure, is pushed together, and it makes helium. The helium can then be pushed together and make another element, and so forth. So these light nuclei are combined together to make these. Light nuclei are combined together to make these. Small interruption there. And either one of these can give a tremendous amount of energy that is subsequent to that. This is basically how a hydrogen bomb works. We take, for a hydrogen bomb, we take hydrogen and surround it with uranium and explode a regular atomic bomb, explode this in to get the high temperatures that are approximately the same as the sun, and then the hydrogen explodes by fusion. So we use both a fission and a fusion at the same time in order to achieve this. For this reaction up here, just a regular uranium bomb like was used in Japan, they take 2 pieces of uranium and keep those separate so that this reaction doesn't go too fast, and then surround those with dynamite and explode them and drive them together at extremely high speed so that this reaction then becomes a chain reaction and becomes what is our standard atomic bomb. So these are our 2 sources of tremendous energy. And if we could control nuclear fusion, this would be incredible. This is one of the most sought after things in all of technology. We have spent more money on this than the entire Second World War, and we haven't yet been able to achieve a controlled fusion reaction where we take hydrogen. If we could do that, it turns out that we would be able to have the equivalent for all seawater that existed. We would be able to have the equivalent of that much in gasoline. That means that if you went out and got a gallon of seawater and could use this reaction just with the 1 out of 1,000 nuclei in the water that is heavy hydrogen, then you would be able to get the equivalent amount of gasoline from that. Then we would solve a large number of the Earth's problems. For one thing, we do not have radioactive materials that come from this like we do with our power plants here when we use fusion. And so this is a much safer reaction, but it's much more difficult. It must occur at temperatures close to that of the sun, which is of the order of about 6 million degrees. So this gives you an overview of both fusion and fission and how these reactions are important, both in terms of what happens in our stars as these elements combine with one another, the light elements are fused together, and in fission, like in the Earth. In fact, no one knew for a long time why the Earth was so warm. It should have cooled off. It turns out that it contains a lot of radioactive material, and this material, gradually decaying, keeps the Earth warm inside and keeps the core of the Earth molten. In fact, it's important, I think, to realize, and kind of exciting to think about, that every element we have in the universe was made out of hydrogen and helium, and that originally there was just hydrogen. And every other element, all of our carbon, oxygen, nitrogen, everything we're made out of was made in stars. So everything in your body originally came from a star that finally made that element and then exploded, and then that element was captured later on by our star, which brought it into the form of the Earth where we evolved.